Hi there. I want to talk about Kinetics today, our unit that's coming up here. You can see on this overview tab in our OneNote notebook the schedule and the readings. You've got some review chapters to read, and then chapter 17 is the Kinetics chapter. The exam on that is coming up on October the 19th, which is just a few days away, just a week away. And we're going to pretty much do all of Kinetics on that exam. And then equilibrium will be chapters 13, 14, and 15, and that exam will be right at the beginning of November. You have sapling homework, and you see the sapling homework, the image of that screen there. This is the exam 4 homework. There'll be some other homework popping up for the exam 5 as well. So we're going to go over and look at the first tab here, the Kinetics Introduction, and I want to make a strong pitch for you to take a look at this this website that is the University of Illinois at Urbana-Champaign, and it's an excellent piece of software that was produced by my friend Loretta Jones and other folks there. The reaction rate thing, you see the image of it to the right there, has a nice little introduction to reaction rates and covers a lot of areas, and I think you'd really benefit from going through that if you get a chance. So the link is at the top of the page there. That link is also on our Canvas page. Reaction rates, I call it kinetics. Frequently the book chapter is called reaction rates. It's a little deceptive in that you might think, well, I'm just learning about how fast reactions go. You actually get quite a bit of insight into how reactions work as well. So reaction rates, first of all, they're worth knowing in and of themselves, right? So rate, anytime rate means that, of course, implies a change in something, in this case concentration of our reactant or our product over time. I guess I shouldn't put that in brackets. And change, of course, delta meaning change there. So knowing reaction rates is a good thing. The example I usually give is, let's say we have a graph, we have concentration on the y-axis and time on the x-axis. This is a graph-heavy unit, by the way. Let's say we have some drug that we want to give our patient, and the effective level of the drug is right here at the dashed line. If we talk about that drug, from the time that it's administered to the patient, there's going to be a curve that looks like this. You're going to have two things going on. You're going to have the drug being absorbed and maybe converted into the form in which it actually works. And then you're going to have the consumption of the drug, right, over time. And when do you administer a new dose? How do you decide how frequently and at what level to dose the patient? And so you might decide, well, I want to administer the new dose over here, maybe so that as this curve starts going up, that the sum of those curves, maybe if I take, this part here and this part that goes all the way up to here, that I'm kind of keeping a consistent level of dosing across there to try and maintain the consistent level. And again, basically you're talking about the rate of absorption, and conversion maybe to effective. A lot of times drugs are actually what you take are not the form that do the what you want it to do, but it gets converted to that form once it's in a human. And then you have the rate of consumption, and also maybe you might have some side reactions. You might have the drug being decayed somehow. And you have to deal with that. Now, the other thing that reaction rates tell you, though, is they give you insight into how the reaction happens, what we call the mechanism. And that mechanistic insight is the most important thing probably that we get from kinetics, because it lets us understand at a molecular level what's going on and to do things at a molecular level where we're like designing, this is the kind of information you'd need to understand how to design a new drug, for example, which is a little more exciting in my opinion than just calculations related to dose. I'll make my usual spiel at this point. This is usually a good point to talk about careers. I meet a lot of students who say they want to be pharmacists because they want to create new drugs. Well, pharmacists don't create new drugs. Pharmacists, for the most part, deal with managing the drugs that you're taking and making sure that those drugs are prepared appropriately and are not, there's no kind of negative interaction with the drug. A pharmacologist is someone who tests drugs. So the pharmacologists are the people who are carrying out the studies right now, trying to determine if some of the injections that they're testing that might prevent the spread of the COVID disease, that might immunize us to the COVID disease. So they basically are conducting experiments, often large-scale experiments involving lots of people and or maybe animal samples. And then the people who actually design the drugs are called medicinal chemists, or generally organic chemists who do synthetic chemistry. Now, I'm going to talk about actually how you measure a rate. And again, this is a graph-heavy concept. This is looking at, and these figures are taken from your textbook, we're looking at a reaction. That reaction is the decomposition of H2O2, and I believe that is looking at H2O2 going back to water and oxygen, right? So it's H2O2, hydrogen peroxide, and it's going to water and oxygen gas, and to balance that we have to have 2 H2O2s, 2 waters, and that gives us 1 oxygen gas. So that's our rate of our reaction. So this is a set of experimental data here that we, at different times, we somehow measure how much hydrogen peroxide we have, and you see, after 6 hours it goes down to about half of what we had. After 12 hours it goes down to half of that, and so on. So this data is arranged so that every time period it's having. The rate is defined in terms of the change in concentration and the change in time. So what you've got here in this column and this column are the changes, right? The changes in concentration between the 2 points and the change in time. And the way we define the rate is if we're looking at a reactant, like hydrogen peroxide is in this case, we're expecting the concentration to go down. So we have a negative sign in front of that. And so you see that down here in the graph we have the negative H2O2 divided by the negative T to give us the rate. The T sub O is the initial rate, and so we have a fairly small, well, looks like a small rate. I guess it's not really a very small rate, but a rate that's on the order, of the 10th to 100th of a molarity per liter, or molarity per hour, which of course hour is a pretty big, pretty long time for the reaction to be going on. Oftentimes you'll see those in seconds. So what you have down here below, this is figure 17.3, is you have a graph of these data. You have the actual, data points. So this data point right here is this data point here, for example, and you see that curves, which the opposite of it is that you can have a straight curve. I know that sounds silly, but the slope of the curve changes. We're taking what this is called is the slope at the tangent line. And so the slope at any one particular set of points appears to be changing as we go along, and that slope relates to the rate over here. So that's again related to the negative slope of the curve. Remember that if we're talking about a XY graph and we have some sort of line here, if we talk about the slope of any 2 points on this line, we imagine this little triangle where this is delta y and this is delta x, and we say that the slope is equal to delta y over delta x, which is what we call the rise over the run. And if it's going down like this, it's going to be a negative number, and if it were going up, it would be a positive number. And in fact, we'll see here in a minute, this is a more complicated figure. It's figure 17.5 in your textbook. This is talking about the ammonia decomposition, where we have two NH3s decomposing to N2 plus 3 H2s, and it illustrates the relationship between the rate as it's calculated based on ammonia versus being based on nitrogen or based on hydrogen. And what you see is that, of course, ammonia here, right, so here's the ammonia one, what we see is the rate is going down. It's a negative number. If we look at nitrogen and hydrogen, okay, so here's N2, here's H2, they're both going up, and the hydrogen rate seems to be going up a lot faster than the nitrogen rate, and the reason for that is the coefficients. So we're able to relate these rates to each other, and it works out this way, that if I look at the rate of change in ammonia over time, so delta T, delta NH3 concentration, and if I multiply that by negative 1/2, now the negative is because it's a reactant, the 1/2 is 1 over the coefficient of ammonia. That's going to be equal to positive 1 over 1 delta concentration of N2 over delta T. So where did that come from? Well, it's positive because it's a product, and the 1 over 1, the bottom comes from, that 1 comes from the invisible one, that's our coefficient there. And then the hydrogen is going to be 1 over 3 delta H2 delta T, where the line here, this red line right here, for example, is the delta H2 delta T. That's that at one particular point. And if you try these out, what you'd see is, if we look at the numbers we have here, this is showing up as 2.91 times 10 to the negative 6. So 2.91 E6 is the H2 rate, and the N2 rate is down here. It's 9.7 times 10 to the negative 7th, and then the NH3 rate is negative 1.94 e to the negative 6, and then we'd say that this is negative 1/3 positive 1 over 1, and that's the positive 1/3 there. So that's plugging those numbers in, and if you go through and process those, you'll see that those are pretty close to each other. That 1/3 of 2.91 times 10 to the 6th, so let's see, 0.33 times 2.91 second, comma, that's negative 6, by the way. I've got to get my numbers right. They're all negative 6. Negative 6. That's 9.6. So this number here is about 9.6 times 10 to the negative 7th. So those are about equal to each other. And then if I take 1.96 second, comma, negative 6 and divide it by 3, I get something that's around 6.53 times 10 to the negative 7th. That's off a good deal more, but again, we're looking at probably slightly different points that we're measuring things. So not quite there, but that's probably due to the point at which they're extracting the curves. So what you could be asked is, you could be asked to calculate things like that. Now, the general expression is, if I have this equation where the lowercase is a coefficient and the uppercase is the substance, then what we say is that negative 1 over a, little a, delta big A, and I don't know why I put a sigma when I meant to just put a bracket, delta big A, big T. So the rate calculated based on the change in A with respect to time multiplied by negative 1 over its coefficient, little a, is going to be equal to negative 1 over little b, delta b, delta t, and that'll be equal to positive 1 over c, delta t, and positive 1 over d, delta t. Now, when we talk about what rate equations look like, one of the basic skills in kinetics is being able to determine what the rate equation is. And there's basically two ways of doing it. One is by a method of initial rates, which is going to be, if you look over at the other tabs, that'll be one of the next videos. And the other is using integrated rate data or integrated rate equations or concentration versus time data. That's the integrated rate law tab that we got coming up as well. Generically, what will happen is if you have some reaction, and again, I'm going to be very generic. I'm going to say A plus B going to C, or A plus B going to P maybe, that our rate is going to look like this. We're going to have K, a rate constant, times the concentration of A raised to X, and the concentration of B raised to Y. And A and B are there because they're the reactants. X and Y are the orders. X is the order with respect to A, and we're going to call shortcut with respect to as WRT. Y is the order WRTB, okay, the order with respect to B, and these are experimentally determined. We can't just look at a reaction and tell what those values are. They can be predicted by mechanisms. And we'll learn much later on in this chapter what a mechanism is and a little bit about how to do that. And that's how one of the ways we tell if a mechanism is plausible is if the observed kinetics, the observed rate law, is in agreement with the rate law predicted by the mechanism, then the mechanism might possibly be correct. We would never say it's absolutely correct, but it might be correct. If the mechanism predicts a rate law that isn't consistent with the observed kinetics, then there's no way that can be the right rate law. So here are an example of some reactions here, and you see you have different sorts of rate laws. The first one, we have the reaction of nitrogen dioxide and carbon monoxide, and we see the rate is second order in nitrogen dioxide and apparently zeroth order in carbon monoxide because carbon monoxide is not listed in the rate equation. Second reaction here is the decomposition of acetaldehyde, and that is second order in acetaldehyde. Decomposition of dinitrogen pentoxide is first order in dinitrogen pentoxide. So what looks ostensibly like similar sorts of reactions, both decompositions have different rate equations and thus different mechanisms. The fourth one there, you have the synthesis of some sort of compound, NO2F, and that is first order in both NO2 and F. And then the decomposition of NO2Cl is first order in NO2Cl. And if we have this rate equation, this rate constant, this is also something that is experimentally determined. And once we know what the orders are and we have some data about concentrations and times, we can extract the value of the rate constant from the equation. That rate constant is going to have different units based on what the order is. So one way to diagnose the order of a reaction, if you were given the rate constant, you can tell what the units are. So let's just say that we have a first order reaction. We'll look at that example. So that would tell me that rate is going to be equal to K times the concentration of something X. And if I solve that for K, K is going to be rate divided by concentration of A. Now, rate is going to be in something like molarity per second. Concentration of A is going to be in molarity. You know, rate is concentration divided by time, so I'm assuming it's seconds. So ms -1, same thing as m per s, or m/s. If we cancel out the m's, then we wind up with seconds to the -1, or 1 over seconds, however you want to call it. And so a first order rate constant is always going to have the units of reciprocal seconds, seconds to the -1. And you could work out all these other ones for 0th, second, and third order reactions to get those rate constant units. And you'll oftentimes be asked in problems to calculate the rate constant, and you may have to solve the rate equation this way and calculate it and get the units. All right. So, short little introductory video there, and again, I encourage you to take a look at the video at the web page that I pointed you to at the top of this.